Hi, everybody. Hope you're doing well this morning and your weekend was nice. As you can see, my weekend's been very nice. They sent me to space along with William Shatner, and I'm floating around here. It's a little treacherous, as you can see. Things are blowing up and stuff, but I've always wanted to go, so I'm having a good time. All right, anyway, let's talk a little bit about a test. I think we have to have one eventually. So, as I've been saying, because of the Zoom format and me doing the practice questions and stuff, I am going more slowly than I usually go. So I don't even know what week we're in. Are we at week 4? It doesn't really make too much of a difference yet. I think what we'll do is we will schedule our tests to be taken at the end of next week. And so that will be after Thursday's class. It will be posted probably Thursday midnight through Sunday midnight, something like that. And you will be able to take the test at your leisure, given that it's 80 minutes long, and it will be open book as we've been discussing and all that sort of stuff. It will not be in class, so we'll just continue to have lectures on Tuesday and Thursday as we usually do. And I probably will get through most of the material that will be on the exam by the end of Tuesday's class, I would think. I'll be much more detailed about this as we approach the test date. Much of what I'll be discussing a week from Thursday will be on the second exam. Okay. I will talk in much more detail about the exam and the format and the number of questions and all that sort of stuff. But I just kind of wanted to give you enough notice. I'm giving you a 9-day notice before the exam comes up. And if you take it Sunday, it's even longer than that. So, you are, sadly that we are still remote this quarter for big classes, but you are going to benefit from that in your test taking, and that you'll be able to do it open book. You'll be able to do it when you feel prepared in a 4-day period. I think you'll find it very straightforward. Oh yeah, maybe the biggest thing, of course, is we've been getting free questions. I think we'll have maybe probably a fifth to almost a quarter of the test where you already know the answers. So lucky you. Okay, I did want to talk a little bit about study strategies before we continue with today's material. But let me stop and see if there's questions. I see a lot of chat questions have arisen. So yes, we are on week 4. Thank you, Natalie. How many questions are on the test? As I said, I'll be able to give you more detail about that next week, but it will be roughly 50 plus or minus a few. So it's the test this week or week 5. Again, it is a week from this weekend. So the test will be posted at midnight a week from Thursday. Okay, not this week, next week. Any other questions before I get into study strategies? Okay, then let's go ahead and chat about that a little bit. So as you know, both through the lecture content and certainly the last few practice questions we've gotten, this is a very conceptual class. In some ways, some of what we're discussing is much more like philosophy than it is like the psychology courses, at least the psychology courses that you've taken in our department before. This is a class that not only does cover perception, but also covers theory and how to evaluate theories and how theories kind of compete against each other and how they kind of take over for each other historically. So it's a very different type of studying strategy you're going to have to use. You will not be able to memorize for this exam. You're going to have to understand. And what I always recommend for a test like this is the following. When you're taking notes, make sure the notes you're taking are put into your own words. So don't just kind of write down what I'm saying verbatim. You've got to think about what I'm discussing, the concepts I'm introducing, and write in your own words. So you have to kind of, listen to what I say, think about what you think it means, and then write it in a language you understand. Write it in your own language, how you would explain it. And that's almost one of the most important things. being able to explain it. It is, I think, one of the most important things, certainly, where, oh, thank you. Thank you for the reminder. I always forget. I don't know why it doesn't default to that, but thank you. Now we have the transcript. You should be able to understand the material in this first 5-week period well enough to be able to explain it to somebody else that hasn't taken the class. And that's how you should consider. I think we talked about this maybe the first day. If I didn't, it will be interesting news for you. There is very clear research that if somebody studies with the goal to be able to teach material to somebody versus study to do well on a test, they learn the material better and they do better on the test if their goal is to teach. Right. So imagine all of a sudden I said, okay, one of our TAs can't teach. You have to teach this next week section. And you had to go out and learn the material, knowing that you had to then present it in front of, 3 sections of 30 students or whatever. Think about how deeply you'd learn the material. You have to learn the material, not just so you're kind of regurgitating what you read, but so you can teach it in a language that's intuitive to you and use different terms to explain it. And that's what your goal should be for this exam. I recommend that you maybe study with somebody else in the class, but I know this is a little difficult this quarter to do that, so you don't need to. All you need to do is make sure you understand the material well enough so you can teach it to one of your friends or siblings or parents or somebody else that you talk to regularly. Say, hey, let me chat with you about why people kind of rejected the Gestalt approach and kind of moved towards computationalism. They'll say, wow, I can't wait to hear this. Okay, maybe they won't say that, but say, it's kind of interesting. Here are the sorts of things that occurred that led people to be less enchanted with the Gestalt approach and maybe move to the computational approach. And then you can tell them, about the kind of computer revolution and concerns people had over the kind of, kind of ambiguity of some of the Gestalt ideas. And if you can do that in your own terms, without just thinking about how would Rosenblum say this, you're going to do well on the exam. Okay, so that's kind of your goal here. For an exam like this, you want to understand. Certainly you have to memorize terms. You have to know what Gestalt, what that theory is, and Ponzo illusion, you'll see the term come up in the test and all that sort of stuff. You have to know that. But more importantly than that, you have to understand the big ideas. And the best way to do that is to understand it to the point where you could explain it using your own language to somebody who doesn't know this. Okay, good. I can talk a little bit more about that next week, but hopefully that's very clear. Let's see if there's some chat questions. All right. When does it have to be finished by? Oh, okay. Kelly's asking about the exam. Yeah. So I believe what we'll do is we'll post it Thursday night. And you'll have all day Friday, all day Saturday, all day Sunday, and it has to be completed by midnight Sunday evening. Okay. Will it be multiple choice? Yes, as we've said, yes, it is multiple choice. Tests will be open from Friday to Sunday, has to be taken within 80 minutes. Thank you, Nancy. You cleared that up. Absolutely correct. Absolutely. Friday, first thing in the morning, if you want to wake up at 1 o'clock in the morning and take it Friday, go for it. But it will be open then. And you'll have to do it all in one sitting. We will talk about the details of this next class. It'll have to be done all in one sitting. You can't stop and say, oh boy, I need to study more. You got to study. You've got to study for this test, even though it's open book. And we have had problems, not just me, I've talked to other faculty. When you do an open book exam, like many of us have had to do during quarantine, a lot of folks take that as a message that they don't need to study. Oh my gosh, that is so wrong, especially for a class like this. You need to really understand things. You cannot, assume that you're going to have time to look up all or a majority of your answers or even half the answers. You will not have time to do that, especially for a conceptual course like this. Okay, you do absolutely need to study. And I'd say study is hard. Study as hard as you would for a normal class that was not remote. Because boy, if you do that and you're ready to take the exam and you're understanding the concepts, you're going to do superb on this exam. You're going to, getting the high A's, because you have some of the questions and you have an open book format. So just study as hard as you normally would for a regular in-person class, which most of you have had at least some of, right? Okay. Don't be scared, Erica. You're going to do great. Again, I remember what I'm telling you about the best way to study. It's an understanding class. It's not a memorizing class. Okay. You do have to do a little memorization, but oh my gosh, flashcards, I guess they could help if you're really kind of concentrating on the understanding part, but you're not going to do okay just by looking at the slides and saying, okay, this is how I define this term, this is how I define that term. You got to put it together so you integrate it well enough to be able to explain it to somebody else. Okay. Okay. There's some questions I've already answered coming up now about the exam. So I would just recommend that you go back and look at the video from the beginning of the class. I don't want to take more time kind of redoing what I've done. Okay. If we've been doing good in the class questions, is that a good predictor? No. Well, maybe a little bit. Some of the class questions I give right after I introduce the concepts, and you haven't had a chance to really, digest the material, Michaela. So if you haven't been doing well on those questions, I wouldn't worry too much. I would, kind of put those questions aside, study, and then go back to the questions maybe and see how you do. That could be a good indicator. But these questions are just being posted not for you to track how you're doing, but for first of all to understand what type of questions I will be asking, and secondly, lucky for you, to actually have some questions all set with the answers ready for the exam. Okay, don't be scared. Okay, listen, I'm not scared, and I'm in space with all this debris hitting me, so. Not just kidding. I think you'll do fine if you remember how I'm suggesting the study. Okay, good. Let's continue then talking about our material. And to remind you, oops, what should I just do here? We were talking about some of the kind of philosophy of the computational approach. And where did we leave off? And yes. Okay, well, let's start right here. This sounds good. So let me share my slide. We were talking about this kind of deep, cool question about the computational approach. And because what we're after here, remember we've discussed this, potentially this idea of artificial intelligence, kind of being able to use computers to understand how the human mind works, how an animal's mind works, how the processes of the brain work, is a really kind of attractive idea, and one that we continue to use. This is not just from the 60s and 70s and 80s, as we've been discussing. This is now something we continue to use, that we do model the mind using computers. You'll see it's kind of been modified a little bit, but it is a very deep and kind of continuing important idea. That being said, I think all of us have some concerns about whether we can imagine a computer as having an emotional life, a deep kind of thoughtful life like people have, right? That's what all these great TV shows are about. I'm trying to think. There's a great show called Humans out of England that's all about this. It's really interesting if you're into this sort of thing. Of course, there's many Star Trek episodes. There's movies. I know that some of your discussion TAs brought up some of these movies. Her, for example, is one of my favorites. One of the kind of least technically science fiction-y, but hers with oh God, what's his name? Phoenix. Yeah. I'm talking about the actor. He's terrific, and he falls in love with an operating system like Siri, who seems to be able to reciprocate the love. Joaquin Phoenix, right? And he falls in love, and the question is whether it truly can be reciprocated, right? Whether a computer-based system that is very sophisticated can truly have that sort of feeling, and that's kind of the general idea we're talking about now. But we're getting a little bit more specific to the things we're discussing in this class, and it's really about understanding whether machines can know. And we talked about this in the context of the Turing test, whether we can continue to use the Turing test as a way of evaluating whether machines know. This was something that Turing had suggested, that if you can be fooled into thinking that you're interacting with a person rather than a machine, then for all intents and purposes, Turing would say that that machine understands what you're saying. Now, I'm not sure we're all comfortable with that, right? But we can, we have many examples, even if conversational computers don't pass a Turing test completely, although they're getting very close, we do interact with machines as if they do have desires and goals and understanding of things like chess and Jeopardy and other sorts of kind of games that we might play with them. We approach them, even though deep down we know we're dealing with a computer, we approach them as if this machine wants to win. Also with video games that we interact with, action games, that the characters kind of want to win, knowing still in our heart of hearts that it is a computer system that is guiding those characters, right? So we do treat computers as if they do have kind of human characteristics in a lot of ways, even if it's kind of prescribed with games and that sort of thing. But the question is whether they truly understand still. And if they don't, what is it that allows us to have an understanding of the world, but not computers? Okay. And if there is a distinction between us and computers, is that an important enough distinction that we should be concerned about a computational approach to the mind, right? Because remember, we're trying to understand all these kind of, sophisticated perceptual and cognitive and psychological processes, assuming that in some ways the brain acts like a computer. Okay. If computers can't really understand, what is it that distinguishes them from us? Okay, we do believe we understand. And is that distinction enough for us to be concerned about using a computer model to understand the mind? So that's what we're dealing with here. And we ended up talking about this idea of this Chinese room, which was a scenario that John Searle in 1980 had posed to folks that were approaching psychology from this computational approach. He said, let's think about what a computer is doing, and let's think about it in a kind of fanciful scenario that really will get to the heart of what a computer is doing. And so we talked about me being in this little room with a little doggy with little shorts on, and I am my whole job, what keeps me busy, what keeps me out of trouble, is manipulating what seems like strings of what I'm assuming are Chinese characters. So here comes the Chinese characters. They're slipped under the door. I look at the characters, the strings of them. Sometimes there's strings of say 10 or 15. Sometimes there's 2. And my job is just to take all those different characters and go to a book that's also in the room. I should put a little book in here next time. And I look up in the book based on all these Chinese characters that I've just been sent. What should I do next? And all it says, if you get these Chinese characters, okay, I get a list of Chinese characters. I see this on a page in the book. I get a list of Chinese characters. There they are. And there's an arrow, and I see a list of another set of Chinese characters. And my job is now find those Chinese characters in the stack of Chinese character paper I have and pass that out outside the door. So I'm getting, I don't even know if these really are Chinese characters, but I'll assume they are. I'm getting Chinese characters that are coming under the door, and then I'm passing them out back under the door, a new set of characters, right? And I have no understanding of Chinese, right? I have no understanding of whether, in fact, these are Chinese characters, right? I'm just very simply manipulating symbols, right? But I have no idea what these symbols mean, right? It's purely formal. right? The symbols could mean anything, you know, that I don't know what I'm doing. I'm just, here come these symbols, and there go these symbols that I'm supposed to send out outside the door. You're outside the door though, and you say you know Chinese, and you're asking questions. You're asking, what's it like in there? Okay, is it? Are you bored? Are you lonely? And out comes this string of symbols that says, nope, I'm not lonely. I've got a doggy in here to keep me company. You say, cool, let's have a nice conversation with this thing, right? And the thing is, inside, I have no idea what I'm talking about. I have no idea what you're talking about. I have no idea whether we're conversing or I'm sending out, maybe commands for, something to happen outside or something. All I'm doing is manipulating symbols, right? It's a purely formal system, and that's something we had discussed before. That these symbols, to me, have no meaning, but outside, you're absolutely convinced that whatever's there, whatever's in there, understands Chinese, understands the meaning of what I'm asking from the outside, understands the meaning of loneliness, understands the meaning of what is it like, all these sorts of concepts that you're from the outside absolutely convinced that I understand. Okay, the truth is I don't. And so what does this imply? Well, here we have a purely symbol or representational manipulation system, right? That's what's inside the room. That's when I'm inside the room, that's all I'm doing. Manipulating representations. I'm basically, another way of saying that manipulating representations is kind of computing representations. We can use manipulation and computing the same way here. That's perfectly fine. I'm just manipulating symbols, and when I'm in the room, have no idea about what I'm talking about. But you're convinced from the outside I do. Okay. And so a computational system, one that manipulates computations, does computations on representations, these symbols, these strings of Chinese characters, can appear like it understands, even though it doesn't. And so when you start, trying to get insight into how the mind works, how the brain works, with using kind of the idea of any system that can, compute symbols, can be considered, a working processor, can perceive things, can have a psychological kind of association with things, right? If I, from the outside, assume that it has a sense of meaning, I'm wrong, because inside there, it doesn't. And so this is the big question of this problem, right? Of this Chinese room scenario, because we kind of assume that this is how the mind works. This is how the brain works, right? Neurons are firing on and off. They're representing on-off states. They're essentially doing computations, manipulations of representations of the world based on these kind of binary states, these on-off neuron states. That's what the brain's doing. So that's how we can use the computational approach to mind. But now Searle's coming in and saying, you're missing something big here, because boy, that computational system, whether it's the Chinese room, whether it's the computer, or whether it's the brain, does not understand what those symbols mean. These are all purely formal systems. And do we want to approach psychology, cognition, perception, okay, thinking that the system does not have an understanding of what's in the world? Does this threaten then the computational approach to mind? Okay. Does this threaten the computational approach to mind? Because, we've built this explanation based on computation, and now Searle's saying computation ain't going to do it, because you can get a computational system to manipulate strings and act like it understands, even though it doesn't. It's a big deal. I mean, all of a sudden, even if think about not just kind of what we're discussing now, this kind of computational approach that was emerging in the 70s and 80s, right? But what you've learned in other classes. In other classes, whether it's been explicit or not, whether it's your social psychology, your personality psychology class, another cognition class, you've been learning explanations where it's assumed that the mind uses representations of the world. The mind uses representations, mind and brain uses representations of the world and, kind of processes them. So when you've heard the term information processing approaches in all those classes, it's assumed that there's a manipulation of representation somewhere in the mind. And here's Searle saying, it's got to be more than that. It can't just be representations that are like computer representations, because those computer representations don't mean anything. The symbols are being manipulated in very sophisticated ways. We can understand how that's done in the brain. Symbols can be manipulated in the brain and in models of how the mind works and all that stuff. But is that enough for the system to understand? And Searle's saying no. So again, like when we discussed Dennett, remember, and I said, any system that has a homunculus is doomed to failure. All psychologies needs some type of homunculus, therefore psychology is impossible. It's kind of almost what Searle is saying here. So yes, I'm trying to throw you into an existential crisis about your major. I'm just kidding. Just trying to get you to think deeply about these things. That a theory that assumes that representations are processed in the mind or brain has to deal with this. How do the representations get meaning? Because right now, from a computer perspective, we're really questioning whether that's at all possible. It can seem like it understands meaning, but it doesn't. It was a big deal in the 1980s, this problem. And it continues to be in some ways. Philosophers still talk about this. Psychologists less so, but that's okay. It's like philosophers are still talking about this. And it's something that we all need to think about, I think, in some ways as psychologists. So what have people done about this? Because it is threatening in some ways. And people have come back and said things like this, possible solutions to this. One idea was this, that, okay, that person, Rosenblum, as I've been portraying it, inside the Chinese room, might not understand Chinese, right? But in some ways, the whole system needs to understand Chinese, right? So if you take Rosenblum and the book and those sheets of paper, all those things have to understand Chinese in some way. We can say that, yes, the manipulator, him or herself, doesn't understand Chinese, but taken together with the book and those sheets of paper, that whole kind of group of things need to understand Chinese somehow. Okay, so that was one of them. So the entire system understands Chinese was one of the solutions that people proposed to Searle. And Searle said something very interesting. Okay, and let's put me back in the room. So now my job is, okay, I've been doing this for so long. I've been doing this for 60 years. My little homunculus in my head has been doing this for 60 years. And that little homunculus has been around long enough to now be able to memorize all those rules. Okay, so he rarely needs to look up these rules anymore. He sees these strings of Chinese characters coming in on paper, and looks at those Chinese characters, and he'll say, oh, I don't need to go to the book anymore. I remember what I'm supposed to do when those Chinese characters, this particular string of Chinese characters comes in. I grab these pieces of paper and I throw out these Chinese characters under the door. Okay, and I'm absolutely correct. From outside the door, you're looking at it and saying, yep, he's not lonely. He has a little doggy. He's not too warm because he's wearing shorts. Cool. I'm interacting with something that understands. So I've now memorized the book. And, I certainly have these sheets of paper I'm passing out, but they could be anything. I could, use Morse code now or something like that. It doesn't really make too much of a difference. I've kind of now taken on not only myself as a manipulator of symbols, but now I've memorized the symbols and whether the symbols that have come in or the ones that are going out and what to do with the symbols. So now, there I've become the entire system. But I still don't understand Chinese. And that's what Searle's saying, that, okay, I could memorize the rules, I could memorize everything else that's needed here, but I still don't understand Chinese, right? So Searle's saying that's not really going to work either, to say that the symbol manipulator understands Chinese, might not understand Chinese on his own, but the book, okay, along with the symbol manipulator, along with all those sheets, that all understands Chinese. And now just let the symbol manipulator now memorize the rules, still not know Chinese, right? Interesting. So other people say, okay, well, if that's not sufficient, what if we do this? What if we now simulate neural behavior? Okay, so we understand, we believe the brain and mind understands the world. So let's not let Rosenblum, the symbol manipulator, just pass out sheets. Let's make him simulate neural behavior. Okay, so if neural behavior is simulated, what will happen, right? So let's think about how we could do this. Okay, so yeah, okay, we'll have Rosenblum kind of simulate neural behavior, not by a rule that involves passing out sheets of paper, but instead, here comes the string of papers from underneath the door. I look at it, and I, based on what it says, the rule book says, I'm going to now manipulate a kind of ridiculously complex kind of web of pipes. Okay, I'm a plumber, right? Now Rosenblum the plumber, right? So, and I kind of turn on faucets here and there, and that makes water going in one direction and stop coming in from another direction. In other words, I'm kind of, turning on something analogous to neurons. And it's really complicated, and it's a lot of work on my part, and I've got to do it instantaneously. You get the idea. It's hard. It's much more complex. But now, do I understand Chinese any better? No. Do I plus the rule book plus the pipes that are going on and off and shutting the water to flow or to stop flowing, do all of these things together understand Chinese? And so let's say absolutely not. That's not a system that understands Chinese. Yeah, you're simulating neural behavior, but that's not really what's going on here. And so what Searle says is that there must be something special. Let's put it this way. There must be something special about biological systems that are computational, right? Might not be in the neural behavior as we're kind of describing it here, but only biological things can know, right? Only things that kind of evolved, through evolutionary pressures and are made up of dimensions of biology can know what's really in the world. Things that aren't biological can't. Now, on a first, we're going to see that there's an interesting kind of direction to this in our next theory. But at this point, people were not satisfied by that. And so, what does that mean? That's not really. You have to be very specific about what it is about biology that allows us to know, but not computers to know what's in the world. Us to understand, us to perceive the world with meaning, our symbols to have a real meaning where computers don't. What is it about biology that allows this, but not computers, right? And so here's what you can imagine, right? Is Rosenblum the RoboCop. This is the original RoboCop, which is a much better movie, by the way, if you're into these sort of things, than the remake that was out about, 10 years ago or something like that. The original RoboCop, which was in the 90s, I think, is a lot of fun. But you know the story of RoboCop, right? He's a human policeman, and he's in a terrible accident. But what they decide to do is kind of use whatever's left over from his body, for the tissues that have survived, which involves about half his brain, kind of make the rest of him a robot, and a kind of indestructible robot, all this sort of stuff. Okay. So here's why I have this idea of Rosenblum the Robocop. Imagine half my brain is silicon and half my brain is biological, right? It's neurons and all the neural, kind of electrical dynamical sort of system. Does that mean one half of my brain does understand things in the world and the silicon brain does not? Okay, that seems a little far-fetched, but yeah, let's make it even more far-fetched. Imagine this. Imagine I'm talking to you right now, and this could actually work since you're not actually in the room I'm in. I'm in space. And as I'm talking to you, your TAs, unbeknownst to me as a lecturer, the TAs are behind my head, up behind my head, and they've done some surgery. In fact, they're continuing to do surgery. They've, kind of gently opened up my skull here. And as I'm talking to you, they are little by little replacing each of my neurons with silicon chips. And they're doing a great job because you didn't know that, I didn't know that, and I'm still talking to you. And I believe as I'm talking to you, I understand what I'm saying to you. Right? I understand, that I'm talking about this philosophical question and talking about the scenario of the Chinese room. I think I know what I'm talking, and you think I certainly know what I'm talking about, right? But now, as I've been doing this, now about half, nope, now it's 2/3 of my brain are silicon chips. Do I no longer have understanding once I have more silicon chips than neurons? It kind of gets difficult at this point to really, and I think that's a valid criticism, right? Just to say it's only biological tissue that can truly understand seems like it's going to run into some problems. And I think this is a really deep problem. And it's certainly one that we're not going to solve right now, but it comes down to a lot of questions. It comes down to, what truly understands. I mean, it is the mind as kind of the kind of, processes, the computational processes that exist on the brain, the thing that understands. Is the brain the thing that understands? And that's what I mean here by the mind-body problem. One way of considering the mind-body problem is, what we've sometimes discussed as mental process being the mind, and kind of the biological basis for that mental process being the brain or the body. So the brain is the material part of what's going on. So it's considered part of the body. So what understands the mind or the brain or both? I mean, it's a really difficult question, and it's a difficult and now important question legally of all places, right? And you probably know a little bit about this sort of thing. Maybe you've taken a psychology and law class or have talked about this sort of thing in other classes where someone commits a crime and then, as kind of an explanation about why they committed the crime, brings in a brain scan showing that their brain is a little different than a healthy brain, right? And this is happening all the time now, right? Somebody, is a kleptomaniac. They can't stop. They just can't stop stealing things, or maybe they have a gambling addiction that led them to actually do something criminal. And defense attorneys will come in and say, yes, my client admitted to doing this, but it really wasn't an act of free will. They didn't choose to commit the crimes, at least not really, because what caused them to commit their crimes is a brain that is different, a little different from other people's brains. And, we've scanned the brain and we had them, look at things they might steal and look at their dynamics in the brain are a little bit different than somebody who's not a kleptomaniac, right? Who's somebody who doesn't want to steal all the time. So it's not their desire to steal. It's not really their intent to steal. It's just that their brain is different. They're not morally responsible for what they've done. And here we really get into a, kind of really tricky place, don't we? So, it kind of makes us question the idea of whether, we truly make decisions or whether our brain's kind of making the decisions for us. All right. I mean, we've kind of gone down a deep philosophical hole here in a lot of ways, but it's all related, right? So you might be thinking, oh, this stuff's fun to think about, all this philosophy, but here we are faced with some very, very important practical concerns about, what is the cause of crime? What is the cause of mental, challenges and that sort of thing. Right? So it's all related. It's a deep problem. And it's all related to this idea of, whether we can think of mental process as being something different from the processes of just pure symbol manipulation. Okay. All right, so that closes off our discussion of the computational approach. You'll see much of this philosophical discussion will pertain to other approaches. And yeah, it's a bigger picture than just the computational approach, but it really was an important part of the history of the computational approach. So what I'm going to do now is take our break and answer your questions, see what's in the chat, and then we will do our first polling question of the day. All right. Oh boy, people have a lot of thoughts on this. That's great. Joaquin Phoenix, right? Thank you, Isabella. I got the name. You'll find when you get to this age, that's the sort of thing, people's actors' names that you used to always have right there available to you. That's the sort of stuff that doesn't come as quickly anymore, but that's fine. It could be a lot worse. Bicentennial Man. So is that the one with Robin Williams? I'm trying to remember. Yeah, I've never seen it, but I do believe that might be a nice example of one. Thank you, Jenna. Okay, Megan says, if X, then Y programmed by someone else, basically. So I think maybe what you're implying here is that the meaning that occurs in the Chinese room is by the system or whatever set up the book that provided the kind of rules, the translations, that if these strings come in, these strings go out. Whatever devised that system, okay, understood what the symbols mean. And I think that's a good intuition, Megan. I think that's a really good idea if that's what you're saying. The problem is, though, and you probably know this, is that computer systems can actually start creating their own rules, right? So there are many types of systems now. Chess, some of the earliest ones were chess, where a chess playing computer would benefit from experience and actually start kind of setting up new rules based on the experience. And so now you have the development of rules generated by a system that, again, doesn't really understand its symbols. Unless you're saying once it's generating its rules, we have to say it's doing this. If that's the case, then computers understand. Probably there's lots of spell check and that sort of thing learns from its experience on your computer. Spell check, actually, either whether you put it in explicitly that this is a word that we want you to know, spell check, or it kind of learns from just experience, which it will do. At that point, if it's learning and kind of devising new rules on its own, at that point, do we say that it's an understanding system? I don't know. If it is, you shouldn't turn your computer off at night because you make it very sad. It's a really good point, though, Megan. Nancy. Yeah, because it has to be told what to understand. It doesn't just formulate its own understanding, right? But it can generate its own rules. We tend to pick things up subconsciously and formulate an understanding from the representations present in the world. Yeah, but you could kind of program a computer to do that too, I think, Nancy. But yeah, again, these are great intuitions. Phoebe likes philosophy. That's great. Hey, if you guys are into this, every once in a while, there's a group of students in a class like this that get really into this, and I urge you to take a philosophy of mind class or philosophy, like a science class, before you leave. One of my good buddies on campus is Eric Schwitzgable, and he's a world-renowned philosopher of mind. He was actually a student of John Searle, the Chinese room guy, and teaches a great undergraduate course that I don't think you need to be a major to take, and I think you'd love it. Nancy, well, the neurons are simply messengers that deliver the things we know to their appropriate servers in the brain. So if neurons were replaced with chips, then the new knowledge may not be kept, but old knowledge would remain, right? Perhaps. Although if, think about, kind of the hypothetical scenario where you could devise silicon chips that acted just like neurons do. I mean, it's not that far-fetched, and they could do all the processes that neurons do. At that point, though, because they're silicon and not biological, do they no longer understand? That's a good question. Do you mind going over Rosenblum the plumber? Yeah, I really decided I want to be a plumber in my retirement. No, what I'm saying is just that Rosenblum the plumber is the scenario that we actually just mentioned. In other words, people said, well, if you simulate, people that were critical of the Chinese room scenario as being too simple, they said, if you simulate neural activity rather than, use these silly strings of paper, then that system understands. And I can't, I said, okay, let's imagine now we're simulating neural activity with plumbing, with little faucets that can be turned on and off, just like neurons can be turned on and off. Will that system understand? It seems pretty obvious, no. And so Rosenblum the plumber is just a name for the scenario where neurons are replaced with something that act like neurons but aren't biological, okay? It's a similar function, not a completely new separate concept formulation on its own. Yeah, thanks, Nancy. That could be a new form of brain therapy in the future, right? I'd be happy to be your very expensive therapist by being your brain plumber. Okay, that's a great idea. All right, wonderful questions. I'm glad some of you are really interested in this. Here's a practice question that's right along those lines. Should do fine here. So here's your practice question. I'll read it first, then we'll post it. Searle's Chinese room scenario demonstrates that A, apparent understanding implies true understanding. Is that something Searle thought was the case? B, apparent understanding does not imply true understanding. C, any Turing machine can understand what its representations mean. Or D, a computer can feel or truly feel. Okay, think carefully, read carefully. I think you know the answer. Oh, yes, you do. Look at you go. All right, I'll give you about another 15 seconds or so. Again, this means nothing. It should mean nothing to me because it doesn't. How you do? And it should mean relatively little to you at this point. If you don't get it right, that's okay. I just taught it, and that doesn't mean that you've actually digested it, that you truly understand it, which is perfectly fine. You will. But most of you do. Okay. The correct answer is, in fact, the one that you answered most, and that is B. What the Searle's Chinese room story really suggests, according to Searle, is that just because something seems to understand, like the Chinese room, like the computer, like the robots in that show Humans I was talking about, like, I don't know, Data in the Star Trek series, in the Next Generation series, if you're a fan of that Star Trek, just because it seems to understand and may seem to have feelings, seems to have goals, it doesn't necessarily, because, that Chinese room fakes out the folks that are outside. The chess playing computer in some way fakes the, master chess player into acting, at least, like it's playing a human opponent, an opponent that has goals and that sort of thing. But deep down, Searle's saying it's just symbol manipulation and the symbols have no meaning. So that's the answer. So A is incorrect. Apparent understanding implies true understanding. Nope. Things can seem to understand and they absolutely don't. C, any Turing machine can understand what its representations mean. Nope, that's not right either. All these things, if we set up the Chinese room to work on a binary system, I guess actually when it's doing the plumbing, it's kind of working on a binary system as a Turing machine would. Still not understanding, so not any Turing machine. For some reason, it seems like most can't, in fact. And finally, computer can feel. No, it might appear to, like in that great movie Her with Joaquin Phoenix. See it if you haven't. It's really impressive. Psychologically, I think you'll find it very interesting now. It can seem like it. You can fall in love with Siri. You can fall in love with the operating system in Her. And I hope that it feels the same way back. But if it's symbol manipulating, Cyril's saying, if it's just symbol manipulating, the symbols don't have any meaning, how can we say it feels? Okay, great. Any more questions before we shift gears a little bit? You did good on that. Okay. Oh, okay. Is the name of the movie She, not Her? Oh, I'm sorry if it is. Okay. So Jenna says she's, oh, I don't want to give that up. Her, it is Her. Okay. Don't read that if you don't want to spoil it. But, you know, even if you knew that, I think it's still really worth seeing. And you're going to say, this isn't really science fiction. You know, there's nothing kind of very modern looking about it and everything. But boy, they really nail the idea of the, you know, the Turing test in a lot of ways. Maybe even more than that. What was that movie that came out? Ex Machina. Maybe some of your TAs might have talked a little bit about that. That's all about the Turing test. That's very explicitly about the Turing test. But I think that in some ways Her actually addresses it with more heart. So I think it's really interesting. Yeah, I really like Interstellar too. Phoebe. Okay, terrific. Let's go ahead and go back to our slides and start a new theory. This will be the next to the last theory that we'll be talking about. We'll be talking about the last theory. Next class will probably introduce that. The theory we're going to talk about now, you're going to see it is related to the computational approach, but it has some differences from the computational approach that I think you're going to find really interesting. It is going to start off actually using one of the models we discussed in the computational approach. So this approach is called connectionism. And you'll see why it's called connectionism as we introduce the early concepts of the theory. But it's going to deal with representations and manipulation of representations, but in a very different way from how the computational approach did. And we'll be talking about this today, how the connectionist theory and the computational theory are distinct from each other. You know, it's going to take a little while to understand this. In fact, I'm asking the TAs to go over this a little bit with you more tomorrow, which will help. The idea is that, again, we're dealing with representations, and the representations can be representations of you know, kind of the more elemental parts of a stimulus as it comes in, you know, features, that sort of stuff. But the way the processing occurs is very different and might actually help with John Searle's argument a little bit about what can understand. You'll see why later, just so you know we're not completely leaving that idea of the philosophy in the Chinese room. But what we're going to start with is this, a parallel processing model we saw before. Now, I didn't talk about it as being parallel processing at the time, but you remember this. This is just one of the ways you can kind of set up a feature detection or a feature analysis sort of system. We first introduced it in the computational approach, but we're going to reuse it here. And just to remind you, we talked about units that might look at the stimulus as it's first coming in and try to recognize whether what it represents. Here's a unit representing a vertical line, whether it's in the stimulus, right? Here's a unit that represents a semicircle. Is that in the stimulus? And depending, imagine it's looking at the letter R, right? A big letter R. This unit says, hey, yeah, there I am, and kind of then passes that information on to another set of units that's in the middle layer that represents letters in this case. Okay, I'll just review for you. It's a parallel process in that these units are all kind of looking for themselves in the stimulus at the same time, in parallel. Okay. So, you know, a computational approach doesn't need to be like that. But there are types of computational approaches that are, and this is one, right? So all the little units here are looking in the stimulus at the same time as the vertical stimulus unit is looking at the input. The semicircle one is doing it at the same time. Okay, we're doing it in parallel. And in fact, you know, at the next level, the unit that represents K and the unit that represents R and the unit that represents P is being activated more or less at the same time in parallel. Okay, that's what's meant by parallel processing here. Should be pretty straightforward. Cool. Okay. There's something else I want to mention about how we first set this up, and that is that the way that this is portrayed mostly here is that these units are kind of sending their excitement up to the next level, right? So here's the semicircle. It's sending its excitement up to the letter R, saying, hey, guess what? I think I'm in the stimulus. Okay, isn't that cool? And I know that, you know, I'm part of you, so we might be looking at an R. And at the same time, it's sending up this information to the unit representing P. You know, I'm seeing myself in the stimulus. I'm a semicircle and I'm part of you, you know, unit P. So we could be seeing a P here, and we could be seeing an R here. And that's all true of the vertical and the slanted lines and all that sort of stuff. Okay, so basically, based on what you're looking at here, I'm sending up my excitement from the as a lower level unit to the next level. Okay, we're calling these excitatory connections, and I'm sure you've learned this in other classes, right? You know, when you talk about neurons, neurons can be excitatory or inhibitory. Hopefully you remember that from your intro class. And the way I've discussed it here so far is just in terms of influences that are excitatory. I'm here, right? Look at this is actually a little limited here. So this is a slanted unit going this way, and I can tell K, hey, I see myself in the stimulus. Oh, wait. Oh, no, in this case, it wouldn't. All right, let me think about how I can do this maybe a little bit more straightforward. No, I can't. I got to do this. Oh, okay. All right, no, let me do it this way. Okay, so let's go back to our friend, the semicircle unit. The semicircle is sending up information to P and information to R saying, yeah, I see myself and I'm part of you, so we could be looking at these. You should start getting excited. And at the same time, it's not sending any information to K because it's not part of it. But what it could be doing, actually, it could be sending inhibitory information, but we'll talk about that in just a second. The other thing that's happening is a one-way flow of information. The excitement goes from the lower level up to the next level, up to a level that then it gets the decision made, right? It's a one-way flow of information from the bottom to the top. Cool. And then finally, something else I wanted to point out about this is that the communication, the influence, the excitation goes between levels, not in units within levels. Okay, so while the vertical line is exciting R and P, okay, it is not doing anything with the semicircle. It's not even necessarily aware of what the semicircle unit is doing at all, right? And the same here. And then at the next level, R is looking to see whether it should be excited, as is P, but there's no influence of what's going on R directly of what's going on in P, and on for K as well. Okay, so there's no communication within a level, or what we call intra-level communication. That just means that there's no communication within a level of units. That's all that means. Nothing too fancy here. Okay, so that's what I wanted to do, is just kind of portray what we were talking about and kind of identify some different characteristics that we hadn't mentioned yet. But now we're going to kind of fiddle with this. Now we're going to we're going to make some very small changes, but changes that are going to have profound consequences for how the system works. Okay? And it's going to allow us to move from a very simple kind of computational approach to this connectionist approach. That's going to, as you'll see, be very different. So we're going to make small changes, but together they're going to have profound consequences. So here's what we're going to do. We are going to add, first, inhibitory connections, right? I kind of anticipated this before, where before I said the semicircle was exciting P and exciting R because it was part of P and R. It could actually, at the same time, send some communication out to K, telling it, hey, listen, I see myself in the stimulus. I see a semicircle in the stimulus. You don't have a semicircle that's part of your structure. K doesn't have a semicircle in it. So I'm telling you, I don't think it's you, K. Sorry, this time it's probably not you. And that would be an inhibitory sort of influence, right? And that's often how it's represented in these figures. Maybe you remember from your PSYC. Sometimes actually it's done different ways, but in this figure, the dot will be an inhibitory influence and arrow will be an excitatory influence, right? Okay, cool. Now look what let's see. Let me get another one here. Yeah, okay. This is the unit that represents the slanted line going down this way and saying, oh, I see that. I see that. So I'm going to tell R, right, that it could be the letter we're looking at. And I'm going to tell K, yeah, because K has that same slanted line as R. Then it could be K, right? So K is getting some excitement here. Okay. But at the same time, because I'm seeing my slant there, I'm also telling R, right? Of course, right? But because I see a slant there, I'm telling P, I don't think it's you because you don't have a slanted line in you, and I'm seeing a slant in the input. Okay, so there's another inhibitory influence. And making this change is going to, allow the system to kind of have more subtlety in terms of, how much each of these units get activated. They're not just being activated by excitement. Now they're being activated by, in some ways, disappointment or inhibited. And that's going to make them get less excited, right? So, P now, if it's, K actually, I'm using the stimulus input as R. This isn't necessarily portraying all that. But, this semicircle is saying, I don't think it's you, K. K is getting excitement, but it's actually getting a little bit of a suppression because it's getting this inhibitory influence from the curve, right? So now how excited K, P, and R actually are, right? How excited they have become is dependent not just on the excitement it's getting from the lower level, but also the inhibition, the suppression it's getting from the lower level. Okay, let's continue with this. Let's add some other connections. Let's allow there to be top-down information. And now what we're going to do is we're going to have another level, okay, that is going to represent words. Now, there's lots of different ways we could do this. I'm trying to make it kind of intuitive for you now. Imagine that, this is a more sophisticated system that we've just, introduced than the one up here, right? It's more sophisticated. And we're going to have another level that actually represents words. And this level that represents words, okay, is going to be able to kind of feed back, kind of provide information going from that top level down to a lower level. That's going to, in fact, in some cases, excite that lower level, and in other cases, inhibit that lower level. Don't, take this particular example too literally, but the idea is this. As R first gets excited from that curve, it actually will excite the letter R that's in the word red. So now what we're dealing with clearly is not just a stimulus that's a single letter, but the more typical stimulus that's a word, right? And R is going to excite the word red because it has an R in it, right? But if I'm getting evidence that R might be that first letter, it's going to inhibit the word pet because pet doesn't have the R in it, right? So it's telling this word, yeah, we could be looking at this word, and it's telling pet, I'm not sure it's going to be pet because there's no R in it, and I'm getting evidence that there's an R in that stimulus, okay? At the same time that's occurring, we're making this kind of much, more sophisticated now in some ways, or complex. We'll say making it much more complex. These units are looking, say, at the first letter. There could be a whole other set of units that's looking at the second letter. And that's all occurring at the same time, as well as another set of units that's looking at the third letter. And that's all occurring at the same time. All this is happening in parallel. So the amount of excitement these words are getting, okay, is not just dependent on what the first letter is, but it's dependent on what the second letter is and the third letter is. And all this is happening at the same time. And it said my connection is unstable. I'm hoping it's stable now. Oh boy, I got a lot of chat.
You're back now.
He's back. Yay, he's back now. It's frozen. Oh boy, how much time did I miss? Oh, just a couple minutes. Okay, you thought it was you. No, it's always me. I take full responsibility for whatever is going bad in class. Thank you. All right, I seem to be back. Hopefully, I'll go back to what I was just discussing. What I'm discussing is that, when we look at a word, the idea is that all these little processors aren't just looking at the first letter, they're looking at the second and third letter too, if it's a 3-letter word. All this is going on at the same time. Each of the letters in the word are being activated. Okay, it's not like we're necessarily deciding here before we start activating these units, right? This is an unfinished process at each of these different levels. All of this is going on at the same time. So if there's, say, evidence that the second letter is E, kind of still emerging, we're not sure, and that the third letter is D, then the word right can say, I'm getting more and more confident it's me. So I'm going to tell that unit down here, R, that, hey, you should be a little bit more active because I think we're getting evidence that it's us. Okay, so that's top-down processing, top-down influences. And it doesn't show it here, but that can be not just excitatory, it can be inhibitory too. Make sense, right? So all this is going on at the same time. All of this is kind of floating around at the same time. Finally, we're going to do one other thing. We're going to tweak this model up here, in one other way. What we're going to do is we are going to allow now for communication to occur between the units within a level. We're going to bring in intra-level communication. And that intra-level communication can be within the units of any level. It can, as R gets more evidence for itself, it can actually tell P, well, I'm doing really well here. I'm looking like the guy. And it can tell P, I don't think it's you. And so it would probably start sending out an inhibitory influence to P and an inhibitory influence to K. Okay, so this is the R unit that represents whatever the first letter might be in this word that's coming in. And R is saying, yeah, I'm looking good. So I'm telling P, probably not you. So here's an inhibitory influence here. It's not being, I understand it's not portrayed on this yet. And here's an inhibitory influence on K. The same thing can happen up here, right? As this kind of continues to go through its process, it gets more evidence that the first letter is R. All the units that are associated with the second letter say, it's starting to look like it might be an E. Third letter might be a D. I can send, the unit that represents red can send an inhibitory influence out to the unit that represents PET, okay? And that's intra-level communication. Also, I should mention just very quickly, all that can be happening here to some degree too. Oops, sorry, oh, I gave it away. It doesn't need to be necessarily, right? So, these don't necessarily have to be in competition. They, as we know, it can absolutely, be working together, but it could if it wanted to. So I didn't have a figure that showed this easily, this intra-communication level easily, so I had to get a new figure, and this is what it looks like. This is essentially the same figure, but now we've kind of made it a little bit, more complicated. And what this is showing is the same type of thing. Okay, as these units are being activated, right? They are, activating these. It'd be nice if like maybe we could, use color to show which ones are most active and say that these are the units that are trying to determine what is the first letter is. Okay, what the first letter of a 4-letter word is. And there's other, units that are looking into the second letter, and they're also coming in here and influencing the word units here. Okay, but it's the same idea, exact same idea. And I'll give you a couple of seconds to draw this if you want. I'm kidding. You have a copy of it in the slide. In the old days, people used to try to draw it with different color pens, and I say, let's put the slides, let's post the slides. But you get the idea here. It's kind of hard to tell, but some of these are excitatory influences, some of these are inhibitory influences, and it's the exact same thing that you just saw. So look at how different this is from this one up here. It is much more complicated. We've just added tiny little things again. Let's remember what we've added. We've added inhibitory influences, not just excitatory, okay? We've added some top-down influences, and oh gosh, this actually doesn't show top-down influences, frustratingly, but imagine it does, okay? That's an important part. And then it shows inhibitory influences. I already said that, but it shows inhibitory influences within levels. So it's an intra level or intra-level sort of influence now. So we are absolutely, there is intra-level communication within the units here. There's intra-level communication within the units here, which is going to help the system immensely. And all these things together allow for a much more sophisticated, nuanced system than the one that we originally discussed in the context of the computational approach. This is what the connectionist theory is about. So the idea is that we're taking all these little simple sort of units that represent things, that represent features in a stimulus, that represent what a stimulus might be in terms of a letter, and represent maybe what a group of 4 letters might make to be a word. And based on the interactions of these units, there's going to be an emergence of a kind of more sophisticated processing, and as I said, more nuanced and more, I guess, a less destructed influence. Maybe that's not the right word. What can I say? I guess stronger and less fragile, a less fragile system than the computational approach. That's probably the right word. Okay, so what is this connectionist system? Well, it's based on the interaction of simple units. Okay, that we've seen. And the interactions now can be more sophisticated than we've discussed before, right? They can be inhibitory, they can be excitatory. And so that's important. But they are, again, it's an interaction of simple units, as we were discussing before. And the idea here is all these influences. It's kind of a very different sort of thing. Remember when we were discussing the computational approach, we discussed it as kind of going through a flow chart almost, that you're trying to recognize a letter, you're trying to recognize a face, you're trying to recognize, and we used a fire alarm, right? Is the alarm on? Yes or no? If no, do this. If yes, do that. Remember, we were going through kind of yes/no decisions, right? Does it have a nose? Is it a face? All that sort of stuff. Yes/no decisions. This is very different. Okay, what this is doing is it's kind of, all these units are kind of influencing each other as if you're almost like mixing a thick stew or something like that, right? They're all kind of bumping into each other and all that sort of thing. And then you stop mixing, it kind of settles into a solution, right? So all these units are kind of influencing each other, excitatory, inhibitory. Some are more excited than others. And after a little while, it kind of settles into the solution, sounding similar to settling into equilibrium. Okay, now remember, this is getting, if Wertheimer is looking down from Gestalt heaven right now, he's probably pretty excited about this, right? Oh boy, they're talking about this equilibrium thing again. That's cool, bringing in this kind of idea from Gestalt. But that's a better way of thinking about it, not like a yes-no set of decisions, but kind of the system settling on a solution. What else? This is important. We are not really talking about explicit rules or algorithms like we talked about in the computational approach. Remember when we discussed the computational approach, as I said, we were making yes-no decisions based on what state things were in. This is the one I think we used for, the fire alarm. Is do you hear the alarm? Does it sound like an alarm? Yes, no, yes, no, yes, no. Is the alarm over yet? No. Do this. If it is, yes, do that. All these sorts of things, and we can use this again for, our any sort of kind of computational approach. It was pretty clear. It was going through a set of rules, going through a very strict algorithm. Here, it's not really like that. Here again, things kind of get mixed around. And it kind of settles on the solution. It seems kind of a little bit more organic than a strict yes/no sort of, rule-based system. What else do we want to say about this? Okay. Oh boy. Want to make sure I have time for this here. Yeah, I'll say this. One thing we didn't mention yet about the connectionist system is that the connections themselves can change. How much this unit down here influences this unit here, or how much this unit here influences that unit there, can change with experience. So, I'm sorry, we're rejecting this kind of strict rule system, but connection strengths can change with experience. So, how often the system sees the word trip, okay, again and again, will have an influence over how the unit representing the word trip influences the units down here. So in other words, it changes from experience across time, right? How often the system, again, is faced with the word trip, one day versus the next day versus the next day, will change how it influences these units down here. Okay, I probably should break after this, but let me just say this part of it. Imagine this is kind of another way of kind of portraying this. Say now this is a word unit, and now this one up here is a letter unit. Okay, they both get activated at the same time. So trip is activated now, and the unit that represents the first letter as T gets activated. And what that means is since these two units were activated at the same time, the strength between them increases. Let me show you what I did again. Let's look at this. Everyone look at the slide very quickly here. What I'm showing is that the strength between the units increases, right? So then I see the words take again, or see the word trip again. And when that unit that represents trip is activated, it's also the unit that's representing the first letter is T is activated, and that unit, that strength between the units increases more. Again, here comes trip, and here comes the unit representing the first letter of T. And as a result of that co-activation again, the strength between the units increases. And this might sound familiar. This is something that Hebb talked about with regard to neurons, that when two neurons are activated together, shoot, I gotta do the question. When two units are activated together, the strength between the units increases. Okay, we'll talk more about that next class, but how are we doing here? Okay, very quickly, here's your question, just to make sure you have it. I apologize for being late on this. Oh, you know something? I'm gonna save this question. You're gonna get 3 questions next class, I promise. This last question kind of depends on me going a little further in the lecture. No problem, you'll get 3 questions next class. We'll make sure that you have that. Okay, have a good day, everybody, and I'll enjoy a discussion section. I will see you on Thursday.